So Burkhak, would you just like me to begin?
Yes, please.
Yeah, right, wonderful. Okay. So I've got a relatively condensed slide pack, and really the intention is just to let you know what we're doing as a company to decarbonise, to address the issues of the climate emergency as a steelmaker, and how that's feeding through into a product offering, and how that product offering can be used to reduce embodied carbon in buildings. So just very briefly, you'll all be familiar with how the climate emergency is unfolded, either in your own country, but this is a UK perspective. And all I'm trying to do here is just show you where Arcelor Mittal kind of fit into that timeline. So for us, we started to engage probably prior to the Extinction Rebellion demonstrations, which took place in London in kind of the spring of 2019. And we, at that point, issued our first climate action report, which is very much a leap of faith, basically saying, right, we commit to net zero by 2050, and we've got a rough idea of how we're going to achieve that. And it was really nothing more than that. It was that simple statement. 6 months later, we then issued an interim target for Europe, a 30% reduction in emissions by 2030. And then 6 months later, we published a bit of a roadmap for our operations in Europe, so giving a little bit more detail. And then in the summer of last year, we issued our second climate action report, and that scaled up the target for Europe from 30% to 35%, and also gave a global target. So Arcelor Mittal operate globally, so we operate in Europe, but also the Americas, India, Africa. So we've got a global reach, and it really tries to acknowledge the fact that how fast we decarbonise will be a function of the countries that we operate in, and some areas of the world are going to go quicker than others, and that target tries to acknowledge that. Just to give you a very brief overview of Arcelor Mittal, and this is really just from the point of view of how we make steel. So we've got 47 blast furnaces. So we make steel using primary resources, so coke, limestone, iron ore. But we also have electric arc furnaces, so we make steel using scrap as well. And then we have something which you possibly might not have heard of, but something called a direct reduced iron furnace as well, which is a little bit of a different way of making steel or iron ore from primary resources. And then scrap is a big part of our operation. It's a big part of any steelmaker's operation, but essentially we utilise as much scrap as we can in that process. We're signed up to various things which are all ultimately about being a little bit more transparent than perhaps we have been in the past in terms of our emissions to atmosphere, and also our carbon reporting. So that's what those bits on the right hand side try to suggest. It's useful to know how steel making's made today before we start to talk about how we might decarbonise. But most of the steel in the world, probably about 70 or 80% of it, is made in a blast furnace. And in a blast furnace, what you do is you take coal, iron ore, and limestone, and you put that in the top of the blast furnace. And then also down towards the bottom, you generally inject pulverized coal. And that pulverized coal is basically a source of heat that allows the other things at the top of the blast furnace to kind of start to melt and to facilitate a chemical reaction taking place. So iron ore is basically a mix of iron and oxygen, which is held together in a rock format. And what we're trying to do in the blast furnace is separate the oxygen out from the iron. So we need to have something that the oxygen can bind with, and the thing that we use in the blast furnace is carbon in the form of coal. So that's the main function of the coal. It's not really as a heat source. It's there as a chemical reductant so that we can get the iron out of the iron ore. The other thing just to bear in mind with the blast furnace as well is that you don't only produce iron, which you make steel from. you also produce blast furnace slag, which can then be turned into GGBS for the concrete industry. So you're actually making two products in a blast furnace. On the left-hand side, I've got an electric arc furnace shown, and probably about 20 to 30% of the world's steel is made in electric arc furnaces. Most people will associate the electric arc furnace with being something that runs entirely on scrap. And by and large, certainly in the Western world, that's true. But also if you're making iron from the direct reduced iron process, in that process you use natural gas to bind with the oxygen in the iron ore, and the iron that you get out is in a solid form, and that solid iron you then use an electric arc furnace to melt down. So that direct reduced iron, you can melt all of it down in an electric arc furnace, or you can mix it up with scrap as well, and that's a relatively small amount of global production for iron. But we think that that's going to increase quite dramatically as we decarbonize as a global community. And the reason for that is that the natural gas is composed of carbon and hydrogen. So when the carbon binds with the oxygen in the iron ore, it emits carbon dioxide, which we don't want, of course. But when the hydrogen binds with the oxygen in the iron ore, it emits water vapor. And we know, so that's done today, but we know that it's possible to use exclusively hydrogen, so that all that you emit when you reduce the iron ore is water vapor. So that's kind of what we think the future is going to look like for primary steel making. If ever you're looking at products, if ever you're trying to assess environmental product declarations, it's useful to have an understanding of what the embodied carbon factors of the two processes are. So if you make steel in a blast furnace, irrespective of what product you're looking at, whether it be plate, reinforcement, sections, the upfront carbon, the direct emissions to atmosphere, are going to be roughly about 2.5 tons per ton of steel produced. If you compare that with an electric arc furnace, that reduces significantly down to 0.5, which is because you're taking steel and simply melting it down. So the embodied impact is essentially tied up in the carbon intensity of the energy grid that's powering the electric arc furnace. Now, in principle, we could make all products in an electric arc furnace, but it tends not to happen. In the construction sector, the only two things that are made using an electric arc furnace are basically structural shapes, which is basically universal beams, universal columns, and sheet piles, and also reinforcement. So you might ask the question why, and I'm going to try and address that in the next couple of slides. So we've got that electric arc furnace, which really is kind of one version or one variant of the circular economy in action. We're taking steel which has reduced, come to its end of life, we melt it down, and then we turn it into new steel products. We can actually take the embodied carbon lower than the 0.5, which you've currently got today, and we can do that. We can do that now, and all we need to do is basically plug the electric arc furnace into 100% renewables. And if we do that, we can get the 0.5 down to 0.3. So that's basically powering everything that we can using electricity. And that's essentially what the XCarb offering, product offering is that Arcelor Mittal have made to the industry. It's plugging that electric arc furnace into renewables. We can go a little bit further, but we need a little bit of time to be able to do this. But basically, when you make steel, initially you just turn the steel into a solid rectangular block, which is called a billet, a bloom, or a slab, depending on the size of it. To turn that block of steel into product, you then heat it up in a reheat furnace. And this is what this thing is here. Now, the reheat furnace, you can't actually power from electricity. It doesn't provide enough heat to warm the steel up. So we use gas at the moment, But if we were to switch that to green hydrogen, then that 0.3 we could probably get down to about 0.15, and that would probably be about as low as you can go with an electric arc furnace. And then you'd have to think about offsetting those residual emissions. But 0.3 is what you can have today. So why don't we make all steel that way, using 100% scrap with 100% renewables? The reason is that there's a rather large difference between current global steel demand and also the amount of material that comes through the scrap stream. So demand's around about 1,800 million tonnes per annum globally. Scrap arisings are about 600. Now, whether global demand continues at 1,800, whether it increases, there are studies which show kind of both could happen. But even if it were to decrease, it would have to decrease by an awful lot to be able to be in line with the scrap arising. So that's why, as a company, but also the steel industry in general, is prioritising the decarbonisation of primary steel making. That's the clear direction of travel that we need to take. And the good news is that we kind of know how we can do it. So one of the ways that we can do it is basically by working with the blast furnace.
Partly in a meeting.
And we can use something which we've called smart carbon. And that effectively is two things. It's capturing the gases off the top of the blast furnace, and we can either use those gases or we can store those gases. Carbon monoxide is a gas which comes off the top of the blast furnace. We can actually turn that into bioethanol, and that bioethanol can actually then be used as a building block to create plastics. And then at end of life, we can take those plastics back, we can treat them, and then inject them back into the blast furnace as a source of carbon. So we can create another circular loop by using those two processes. So the capture of the gases we've called Carbalist, the converting of the plastics, but also wood into a carbon source to be used in the blast furnace is called Torero. So that's one of the technologies. The reason that we're kind of pursuing that route is it allows us to still continue to manufacture blast furnace slag, which can then be used in the concrete industry. The other process, which I've kind of hinted at in the previous slide, is basically reducing iron ore using hydrogen. And that's where we need a little bit of support from governments and also a little bit of support from industry to supply us with the green hydrogen that we need. The smart carbon processes, this is kind of an industrial scale pilot plant, which is under construction at the moment, fairly well advanced and due to complete this year. So this is in Ghent. So this is your smart carbon technologies, pretty much ready to go live at an industrial scale on one of our sites in Ghent. The green hydrogen process, we're about 3 years away from that happening. So we're in the planning stages now, but basically the way that it'll work is I've tried to illustrate in this diagram here. So essentially we're basically making renewables or entering into power purchase agreements with people who can manufacture renewables. We then need somebody who has an electrolyzer, and then we can power that electrolyzer using those renewables to create green hydrogen. That green hydrogen then feeds a direct reduced iron furnace and basically emits water. And then that iron then goes into an electric arc furnace, which is powered again by renewables. We will need a little bit of carbon to facilitate the chemical process, to turn the iron into steel. And we foresee that being from a circular source of carbon, so probably a wood waste resource. You then got the reheat furnace here, which again would be powered by hydrogen, and then the rolling mills themselves that make the products, they would be powered by electricity. So that is the plan for one of our plants in Sestao. That will produce 1.6 million tonnes per annum and we believe it'll be the world's first full-scale zero carbon plant. That's on 01, 02 emissions, and that's a work in progress now. The electric arc furnaces are already in situ. It's actually the hydrogen reduction of the steel that we're basically working on at the moment. The smart carbon offerings. One of the offerings that we have coming to market is called XCarb Green Steel Certificates. And what we've been doing is basically going around all of our operations and looking where we can save carbon. So currently in one of the blast furnaces on all of our sites in Europe, we've displaced the injection of pulverized coal currently with natural gas. But we also have the option of using hydrogen when it becomes available, and we also have those smart carbon options as well. If we do that, we actually reduce the emissions to atmosphere by round about 3%, and we've actually been doing that in the last 2 years. And if we were to write an EPD, the value on the EPD wouldn't change significantly. It would be quite modest in scale, and we don't think that would have enough value in terms of a specifier, trying to specify a low carbon product. So what we've done is we've actually gathered all the carbon reductions that we've made and then divided those reductions by a factor of 2.112. And the significance of the 2.112 is basically that is the average carbon emissions to atmosphere from a blast furnace in Europe. And that allows us to basically change those carbon emissions into an equivalent volume of, I'm going to use the word zero carbon steel. It's not quite true. It's a little bit of a technicality, but zero carbon steel. So that's one of the offerings that we have. A little bit complex to explain, but I'll try and illustrate with an example shortly. So looking at those things, what does it all mean? Some of you may or may not be familiar with an organisation called LETI. So this is an organisation of engineers, architects, designers, but other people in the supply chain who've basically issued some guidance on how we might create a carbon target for a building at design stage so that it creates a focus in terms of the materials that we use and our approach. And if you were to take an office building today, it would have an embodied carbon of around about 1,000 kilograms of CO2 per metre squared. And they've used that as a starting point and then reduced the carbon budget for the building in accordance with the Paris Agreement. So if we look forward to 2030, the buildings that we're building should have an embodied carbon no greater than 350 kilograms of CO2 per metre squared. The LETI guidance then also breaks that down into the elements of a structure. And what we find is that the superstructure accounts for the largest portion of the carbon. So your frame, your floors account for 48% of that 350 budget. So we can work with that and then actually start to give ourselves some helpful direction in terms of what that means. So if you looked at a typical superstructure on a steel framed office block, the slab would have an embodied carbon of round about 68 kilograms of CO2 per metre squared. Might be a little bit more, might be a little bit less, depending on what you do. But that then gives us an allowance for the frame. And then we can work with that frame allowance to very simply calculate what the carbon intensity of the steel frame might be. So there are two bits of information that you need to calculate the intensity of a steel frame. The first one is that you need to know the steel intensity. So you take the total tonnage of the steel frame divided by the floor area, and that will give you the steel intensity. Now, typically for a multi-story in, say, London, that would be around about 90 kilograms per metre squared. The only bit of information that you need after that is the embodied carbon factor, which you take from an EPD or some other form of data library. Now, if you're looking at blast furnace produced section, a typical value would be around about 2.45. That's from an EPD that's available in the UK. So you take the 90, you multiply by 2.5, and you get a value of 221. but our target for that LETI 23 budget is only 100. So it doesn't look like we can hit it. But if you use the XCarb product, which is made from 100% scrap and 100% renewables, then the 2.45 goes down to 0.333. And so the embodied carbon reduces to 30. So you now have a mechanism whereby you can meet the embodied carbon target for the building. The other way that you can take the whole reduction, or what you can actually do is then start to look at the mix of steel that you use in the steel frame. And the process for doing that is you take that embodied carbon target of 100, you divide it by the steel intensity, which is 90. And then if you use this little equation on the left-hand side, you basically arrive at an average carbon intensity for the steel that you use in the building. And then again, if you use this little expression that I've got done on the left, you can actually calculate a percentage of XCarb product that you need to hit the target that you set yourself. So that's another way that you can use it. A quick win. So this is me thinking that we've got a mixed group on the call, and some of you may not be involved in design. It may be that you're further down in the supply chain, involved more with procurement. But one thing that you could maybe challenge your design team with, is particularly if you're looking at multi-story construction, is the grade of steel that they use, particularly for things like columns. So I apologise because this is a little bit technical, but we are just multiplying two numbers together. So most columns will come as a weight per metre, and in this case I've chosen a section which has a weight per metre of 340 kilograms per metre run of beam. And to calculate the embodied carbon in that section, you just multiply by the embodied carbon factor. So here I've taken 2.45. But if we change the grade of the steel from 355 newtons per millimetre squared, which is the amount of load that the steel can take, we can increase it to 460. And if we do that, the column size comes down from 340 to 235, and we save 31% in weight. If we leave the steel provenance the same, then you'll save the same amount in carbon as well. So again, this is just trying to get across that simple message that if you save the amount of material that you use in a building, you will save a similar amount of carbon in direct proportion if the provenance of the material that you're using is exactly the same. But if you were to use XCarb, then that 576 could reduce to 78. So there are things that you can do to reduce carbon, and this again is something that you can do today. This is not looking towards the future. This is something that can be done now. 460 grade material has been around for about 30 years, and it's there to be used. Here I'm just looking at a shed, so a typical single-story building, and this is looking at the embodied carbon of all of the different components. So we've got the cladding. Again, all we need to know is the weight of the cladding. So a typical sandwich panel would be 13 kilograms per metre squared. If you look at a typical EPD, the value of that would be 2.72. You multiply the two numbers together and you get the embodied carbon per metre squared for the cladding for that building. You can do the same for the purlins. You can do the same for the frame. And you can also do the same for the slab, which is made of concrete. You add all those up and you get a total. And what you find is that 50% of the embodied carbon is actually in the steel frame. You can then start to play around with the XCarb offering. So we've got the green steel certificates, and there's a calculation process that you can go through there. But the 35 you can reduce down to 8 with the purlins. The 12.9 goes down to 2.3 with the frame. The 110 goes down to 15, and the slab, I haven't done anything with the concrete. So what you see is that using these things, you can actually significantly reduce the embodied carbon in the frame. It's just about knowing about what products are available and how to tap into those. So again, that just gives you an indication of how the percentages have reduced. This is the final slide, so I appreciate that I've rattled through that quickly. If anybody had questions or wanted to talk about it independently, not a problem. But one of the things that you can also think about is also thinking about where you get the steel from. So there is a specification called responsible steel. It's a broad environmental, social and governance standard. So it's looking at, where you get the materials from to make the steel. It's ensuring that you've got the right conditions in terms of the people that you employ in your business. And it's also got the governance aspect, making sure that you do things in a legitimate and responsible way. But one of the clauses in this standard is a Paris clause. And it's Principle 8, which basically says that if you're a steel producer and you have been certified to responsible steel, that somebody's basically looked at your decarbonisation roadmap, looked at the targets that you set, and then basically ratified those targets to ensure that they're aligned with the Paris Agreement. So again, something that you could ask for, and that is it from me.
Thank you so much, Walter. Does anyone have any questions?
That was really interesting. One question that is a bit of a random one. Why Spain?
Why Spain? We've got sort of sites all over Europe, and we can actually make the investment to put in the DRI EAF plant. Costs about £1 billion. $1 billion to put in a DRI EAF. So there's quite a lot of money there to spend up front. But what we're not really experienced at is the power generation and the production of the hydrogen. So we see our role in that process about creating the demand, and to be able to do that, we need support from kind of governments, but also the local industry. So the reason why we've gone Spain is A, because they're a hot, sunny country. B, we already have power purchase agreements in place with some of the energy suppliers there, and it's a relatively easy door to push against to develop that further. And the government, the Spanish government, have been very supportive in terms of our aspirations there and providing the necessary framework to allow an electrolyser to be built. So the reason Spain is that we can produce the green hydrogen. The key issue for us is the green hydrogen. If we can get green hydrogen, we can decarbonise tomorrow. But I'm being slightly glib with my words there. We need to build the plant, of course, and the plant will take a year to design and probably 2 years to build. But that for the steel industry, that's basically tomorrow. So I don't know if it comes across as ambitious to you. It maybe doesn't, because you probably want it quicker. But actually to roll that out in 2025 is quite a challenge. In terms of us hitting our target, our 35% reduction target by 2030, we need to spend about $10 billion. We've committed $5 billion. That's by 2030. We've committed $5 billion already, and that essentially is DRI EAF facilities. The one in Spain, but we've also got plans for one in Ghent. There's also one in Germany, in Bremen. There's also one in Belgium, in Ghent, if I haven't already said that. And we've also got plans for one in Dunkirk as well. Also got work occurring in Canada at a plant there. And there's still obviously a little bit of work to look at where we spend the other money on the other plants, but that's kind of committed. The funding's there. We've got the financial agreements in place. It is literally a case of just getting the things built now.
I think sounds really impressive.
Yeah, I mean, again, I don't know if this is helpful to you, but generally our sites basically run 2 blast furnaces. So the general process is we build the DRI EAF facility and we take one of the blast furnaces out. So it is a little bit of a hedging strategy. which is why we're also looking at the smart carbon as well, because we've also got this issue with cement. The steel industry actually produces quite a bit of cement in the form of GGBS. So it's kind of trying to manage that transition process in a sensible and rational way. So thanks for the question, George.
No, thanks for the answer. I actually sent a screenshot to my brother. He works for RWE over here in the UK, and that was sort of a question from him. But I'll be passing on your details because he'll be really interested in this. I've sent a few screenshots. So yeah, thanks, Walter.
Yeah, no problems, no problems. I know I did numbers there, and I appreciate that many of you might not be designers and you don't get involved in that sort of stuff, but is it helpful to see those? Because sometimes life cycle assessments can be very complex, very inaccessible.
Walter, I think you did an excellent job of simplifying it and communicating it really, really well. I thought it was an excellent presentation, so thank you. And you're going to laugh at this. As a procurement guy, numbers aren't my strength, but that was brilliant. That was really good, easy to digest. Really, really good presentation. I haven't got any questions.
Excellent.
Why aren't we buying this stuff more often and more frequently?
Well, that's good. The trick in all of this is embodied carbon factors, choosing the right one. My personal view is at design stage, a lot of people use something called the ICE database. So it's the inventory of carbon and energy. And you'll find that uses averages. Now, some of the averages I'm okay with. So if you take, say, plate, the average there is probably quite reasonable because most plate in the world is produced using blast furnace. But as soon as you start to get a mix of blast furnace and electric arc furnace, my personal view is that that's not an average because you have two completely different processes. So if you see a value that's close to 2.5, you know that it's blast furnace product. If you see a value that's close to 0.5, it's electric arc furnace product. Anything in between is a mix of those processes. And so that what that means to you is that as a procurement person, that means you have choice. So you can either say, right, we'll just use those averages and the market can decide what the embodied carbon in my building is, but you have absolutely no idea. It could be closer to 2.5 as an embodied carbon, or it could be closer to 0.5, or you can start to take control and put an amount in your specification.
Yeah, I think it's just linking nicely to the workshop we've just done. It comes back to better procurement equals better specifications for me, and being very, very clear in driving carbon down in those specifications. Because ultimately, we buy whatever people tell us to buy. We're not the specifier, and we facilitate the buying process. But the closer we get as procurement professionals to you as suppliers and our designers in specifying products with lower carbon contents, the better. I think it's that simple.
You do have to be responsible though, because you do have to accept that we are trying to transition as an industry, and as a company we're trying to lead, we're trying to push the others into action, and it will be difficult for some steel manufacturers. And I'm thinking particularly of the UK, where they don't seem to have the support that we've seen in other countries. Yeah. So whether you want to be brutal and just say, I don't give a jot about that, it's about the climate emergency, we're going to go as fast as we can, there are people that can do it, or whether you take a broader view and think, well, actually, if we put some businesses out of business in the UK, that means jobs and all those other social factors. But all I'm concerned is that you have the facts to be able to make that decision.
Yeah, I think you're right. I think that it's always about balance, isn't it? And my mission is to just be clear on what escalating carbon as much as we can, but you can't do the ride roughshod over social value or economic value. I absolutely understand that.
Yeah, good. George has his hand up.
Yeah, I also thought it was an excellent presentation. One of the interesting things about it is that the way you've broken that down, it's giving us the information that we can perhaps use to make choices.
Yeah.
Because I think far too many of the initiatives at the moment are about carbon reporting, which is too late.
Yeah.
We need to be able to get the information to people like Gareth, for example, so that he can perhaps influence the designers, so that the process itself to be able to make the appropriate changes. So, yeah, excellent. I really enjoyed it. Thank you.
No, thanks, George. I mean, just one final comment from me, really. And I know I've seen presentations from other organisations, and the thing that people need to be, I'm going to say, called out on is the embodied carbon factor. That's what people really need to understand, because I think lots of people are just using these data sets and taking the data there as given. And you really need to drill down a bit. If you're really going to root the problem out and understand it, you need to drill down a little bit. And that's probably where I could help you on the steel side, because I've spent the last kind of 18 months, 2 years, surrounded by EPDs of all different steel products, trying to make sense of it all. So happy to take any calls if anybody has any more detailed questions. But thank you all very much for your time. I think I've gone slightly over the half hour, but hopefully it's been of value to you.
Absolutely. Thank you, Walter.
No, thank you all.
Thank you. Thank you, Walter.
Thank you.
Excellent. Well done, mate. That was brilliant. I thought it was a really good presentation.
No, thanks for that, Gareth. I know I sometimes get criticised for doing numbers, but I think you need to do them.
Yeah.
And they're two simple ones that most people relate to. You know, it's no different to calculating your wages, is it really?
It's fundamental. We said it in our presentation. If you don't get into the numbers, none of it really works. So you have to tackle numbers. I thought it was brilliant, mate.
No, good.
Bertha, I just wonder if is there a password to the recording?
No, because it's my university account. That's why you can't reach it, but I can send it separately.
Okay. All right, excellent. All right, no,
Okay.
I'd like that as well, if that's possible. I think the only way of doing it is to download it, isn't it? That's the way Teams
Yes.
works. Yeah.
Yeah.
If you could do that, that would be, because I found it extremely helpful.
Yeah, I definitely
Yeah.
want to go over that one again. Certainly, Walter's was brilliant. I just need to digest it a little bit more. That's all.
So, I mean, again, I know you guys are busy guys, but I went through that at a rate of knots, or it felt like I was going through it at a rate of knots. If you just need a little bit of time to slow it down, that's not a problem. Just give me a shout.
I think as feedback, I think half an hour is just not long enough. At 45 minutes to an hour would be better for as a presenter. That's my feedback to you, Bertha. It needs longer.
Yeah, that's right.
I think the thing is, you've seen what's been offered now, Gareth, so you're hooked. But if I'd said to you, I need an hour, you would have told me, no, you've only got half an hour. So.
Exactly. Yeah. If only I was buying steel, but yeah, we'll talk. Excellent.
Wonderful.
Thanks,
thank
guys.
you. Thank you all very much. Appreciate that.
Thank you. Bye.
Okay, take care.
Bye.
Bye now. Bye.